It's buffering at the moment.
Do you want me to test?
We did already.
Okay.
Yeah, we did when you were practicing. It's buffering at the moment.
How many please? So much. Oh, just- oh. So, like, add the slide.
Okay. Wherever you would like to be.
Yes. Usually we are live, so, yeah.
They're starting, you go up. The first two people are when? Also, we should all introduce them. Actually, we should all start up there. So we can all-
Yeah, well, I'll start.
It's not broadcasting.
I can use my laptop.
Oh, there it is.
Yeah.
Okay. Let me see.
Yeah, 30 more seconds.
Looks like lots of people are joining us on YouTube.
Hopefully.
I know that there are some. Are you guys good?
Yeah.
Okey-dokey. Okay. Hello. Thank you guys for joining us this morning. Having a few faces in person is really helpful. So be prepared for lots of eye contact and maybe to pose some questions at the end if you could. Welcome also to those of you that are joining us live on YouTube. We are at the Canadian Light Source, and this is Halifax Grammar School, and they have participated in Students on the Beamlines. And with that, I'm going to turn it over to them to carry on.
Right, good morning, everyone. Hope we have all a good start today, and we can't wait to make it even better. Now to our project. Our research question is, how do different concentrations of lead in soil affect the lead absorption in dandelions? And as an aid to help further understand our project, we will correspond our story to the journey of a pizza through a restaurant. As you probably have noticed, we have the Hawaiian pizza, our expectations, the dandelion salad, and our lead solutions. And this would be what we learned, and basically it is our results. We would like to acknowledge that CLS is on Treaty 6 territory, traditional homeland of the Métis. We would also like to acknowledge that we are from the Mi'kmaq, the ancestral and unceded territory of the Mi'kmaq people.
Okay, so just a little bit about us. So we arrived from Halifax, Nova Scotia, which is a province on the east coast of Canada. We're from the Halifax Grammar School, and we comprise of grade 11 and grade 12 students with an interest in research and science. Unfortunately, as remembered, Lillian was not able to come onto the trip, but she was a big help back home. And just an interesting fact, although Nova Scotia people may think that Nova Scotia as fishery as the #1 industry, it's actually forestry.
So our team, we're just gonna introduce ourselves. I'm Singhan Lee, I'm in grade 11. And I really enjoyed this synchrotron because I actually learned a lot about the scientific process and how we actually determined and the process of coming to a conclusion.
Hello everyone, I'm Raj, I'm in grade 10, and grade 11 as well.
My name is Ziqing, I'm in grade 11 and enjoyed working with all the scientists.
My name's Adam, I'm in grade 12, and I really enjoyed just using the beamline, that was really cool.
I'm Sean, I'm from grade 11.
Bill, I'm from grade 12. I love the process data. It's kind of like a game, finding clues leading to the final answer. I like it.
And I'm Yusuf, I'm in grade 11, and I'm sure all of us learned many valuable lessons throughout this whole experience.
So before we actually get into our data and our results, we would just like to present our process on how we actually got to our research question. So initially, we wanted to look at the element radon because Nova Scotia and Halifax in particular has a big issue with radon and the radon concentrations in soil. So right here is a map of Nova Scotia, and Halifax is right here, right in between the red and dense spots of radon concentrations. So radon is radioactive and is hazardous to humans who consume or come in contact with it. And so we figured that studying radon is important for the safety of the future of Halifax. However, there were a few limitations of using radon. Firstly, radon is, as I mentioned, radioactive, and it has a half-life of about 3.8 days. Our flight from Halifax to here was about 7 hours. So by then, already 10% of the radon has been decayed. And that's a huge amount of data that would be just lost. Not to mention the waiting time we have to use for the beamline. And so all of the radon, or a lot of the radon that we collected would not be usable. And another reason we didn't want to use radon is because it's highly dangerous to utilize without the proper tools, and we didn't have access to those. So we decided to work on lead, which is a different element, but it's the element that radon actually decays into. Lead is stable, unlike radon, and it's also much safer to use because it's not radioactive. So lead is also hazardous to humans who consume it, and it's also why we wanted to look at the absorbance of lead in plants. So as Halifax is moving to a more urbanized and industrial area, food security is becoming a bigger and bigger issue, and dandelions have actually been consumed more and more over the years. And this is important because if the dandelions actually do absorb more lead, then that could lead to lead poisoning, which results in cognitive disorders. And it also leads to negative environmental impacts, perhaps spreading to other plants or even to the wildlife that actually consumes these plants. So as a metaphor to begin, we would like to compare lead to pizza. So I'm sure we can all agree that pineapple on pizza is an abomination of a thing. So we would like to compare lead concentration to pineapple. We want to diminish the amount of pineapple on our pizza, similar to how we want to diminish lead concentrations in dandelions. So when we first started our research question, we had a hypothesis stating that the more concentrated the lead is within the soil, the more it would actually be absorbed within the dandelions. This was just based on intuitive thinking, that if there was more lead in the soil, then the dandelions would absorb more of that lead. So for the past week, we have been at the synchrotron here at CLS to actually sample our data, to use the beamline and to collect and to analyze that data. So for our samples, we actually split the dandelions into 3 different sections, which is the soil, the roots, and the leaves. We did this because we wanted to measure the relative concentrations between each section. And we would know that maybe one section had a particularly more dense and more concentrated section of lead, than the others, and that would be more hazardous to eat and to consume. And to actually scan and find the concentrations in each section, we used 3 different scans from the IBS Beamline here at CLS. The first was the XRF scan, which is a method to figure out the relative composition of elements in a sample. The Zane's Beamline, which allows one to find the speciation of a certain element, and the XRF mapping, which allows you to figure out the physical distribution of concentration in a sample. So here I have a simple sample holder, if you can see, and in the back, I'm not sure if you can see, but there's a small slit here. This is where we prepare the samples, and the XRF Beamline actually just hit our samples through the hole, and it absorbed a certain wavelength, and it reflected light to a detector, which actually gave us our desired data. And for the mapping that I just showed, it actually just took a really small portion of this slit and did that multiple times. So you actually had just an XRF scan of multiple different areas on this sample. So the first method we used was X-ray fluorescence, which is short term XRF. And it allows us to have maps that are highly sensitive and extremely useful for correlating the distribution of the elements present. And in the graph, as you can see, there are peaks, and each peak is correlated with a specific element. And at first, we did extra scan for all of the 21 samples with it. Based on the scan data, we found out that that the concentration is in the order of the peak level, but not in the order of what we watered them. Here we can have a closer look at the graph as shown. Solely the concentration of 120 ppm is located above the 150 ppm one, which shows there is no expected trend. Then we moved on and examined the same graphs for the roots and leaves as well, and the same thing happened. In roots, for example, as you see, 120 ppm has a higher peak than the 181. And here, for the leaves as well, which is the strangest thing happened, that the 2010 ppm does not have the highest peak, which 151 one has. So all of these observations made us more curious about the reason of this happening, and then which led us to try another method and create maps. Oh, I just pressed the wrong thing.
Very good, no problem.
This map of would be the concentration of 120 ppm shows the relative concentration of lead on different sections of the prepared slide that Gogo Singhao showed us. The widest ones that you can see on the right represent the higher relative concentration of lead, and the darker spot shows the lower concentration of the lead. And by looking at this sample, we can see to the left there is a less lead than the right side, where it's lighter. And there's scale bar on the right side shows us there is roughly 20 times more lead in the brightest section to the darkest one.
Okay, so now comparing the 150 ppm to the 120 ppm, we can see that to the left here, it's a lot darker, and throughout the rest of it, we have lighter shades, which means there's higher concentrations of lead in this area, that area, and a lot more in this just one block. So we can start suspect and think that perhaps the samples and the placement of the lead is, well, varied. Similarly, the 180 ppm, where we have the majority of the map showing us how there's pretty much lead almost everywhere except this corner here. So again, this further confirms the fact that, well, if everything is not going to be in like one spot or is not even in a specific way, we know that it is a lot more varied than what we would expect. That was the roots. And then we made maps for the leaves and we got similar results. We have this left side, the majority of the lead, and the right with almost none. As well as the 210, where we had a drastic change. We have this one spot up here with the most, and this should be pretty much black for the rest of it. So we've decided and realized that, well, that means the samples are not homogeneous. And data is not reliable to use or draw conclusions from. That's why we decided we needed to reassess the way in which we prepared samples.
So now we're going to analyze the uncertainties presented in our experiments and the possible improvements that we could fix those uncertainties. So here's a graph of the element distributions in the soil, and the blue bars represent the concentration of lead. If you look at the third row, which is the 180 ppm soil, we can tell that it's very abnormal because the lead concentration is very small, which doesn't match up with our expectations. So we realize that there must be something going wrong when we're watering those plants. So that brings us to the first uncertainty, which is the watering and treatment of plants. So when we're watering the 180 ppm plants, we water it on the leaves instead of the soil. So that might have caused the abnormality of the lead concentration in the soil in 180 ppm plants. And secondly, the mass of soil in each pot were actually not controlled, which could also cause the uncertainty of lead distribution. And additionally, from the photo on the right, we can tell that the plants were actually not in the same growing stage. In the middle one, which is the 180 ppm plants, were actually pretty mature, while the others remain at the growing stage. And finally, the lead was actually not evenly spread out between the soil, so that the concentration in different spots might be different. As for the second uncertainty, which is the cross-contamination, there was some soil left on the roots and the leaves, and they were actually not separated from each other. So here's the microscope picture of the 210 ppm leaves. We can definitely see that there's a lot of soil left on the surface of the leaves, and that could cause great uncertainty because the lead concentration in the soil is way higher than the concentration in the leaves. And here's the XRF map of the lead in 210 leaves. We can see that this spot is 100 times brighter than all the other spots, which indicates that the lead concentration in this spot is way higher. So that proves our idea that there must be cross-contamination must have happened.
So our third uncertainty that we get is actually a lack of samples. As you guys might notice in the previous photos that Sean showed you guys, it's pretty different. Each plant have different conditions, and they're pretty different from themselves. So what happens is actually the plants are like pizzas. They have their own conditions. So for pizzas, even though they could have the same toppings, they could still be different from each other because they have different temperature, different weight, different textures. So yeah, that's why we need basically more samples to average out the difference, the individual difference. So move on to the first improvement. We're talking about cross-contamination. The first solution we can think of is basically get rid of the soil that is on the surface of the sample. So the main idea for the first improvement is basically get rid of soil. So the first step is probably just going to wash the plants before they're made into our samples, so that we can make sure soil is not going to be present in our samples. And the second technique we can use is hydroponics. Hydroponics allows us to grow plants without using soil. They can be grown in solutions. So in this case, we don't even have to worry about soil being left on the surface. And this is also going to be very helpful. We're feeding the dandelions with our lead solution, because in this case, lead will be more evenly distributed in the soil, basically more homogeneous. And then the second improvement we can take is basically growing plants when they're still seeds. Because still from the same picture that Sean showed you guys, the plants have different ages and they're have different conditions. And some of them is like very mature, some of them is still growing. So raising plants from seeds allows us to control their condition, control their age. And then this is basically like making pizza from doughs. You don't want to get pizza like frozen pizza from superstore, from like frozen pizza. You don't want to get those. You probably want to make them by yourself. Use fresh doughs to make delicious pizza. And the third improvement we got is as I mentioned before, more samples for each concentration. It's up one for each concentration. So this allows us to have a larger sample pool, and we can basically average out the random error. In this case, is individual difference of the plants. So we can take the average, and then taking average help us reduce random error.
And as for our last improvement, we need to ensure homogeneity and avoid cross-contamination. We need to ensure that the treatments to all plots are uniform, which means that we need to focus on one specific independent variable, which is the light concentration that we use to water those plants in this case. And it's equivalent to the amount of use for pineapples on those pizzas. However, all the other procedures, such as how you make the pizza and the other ingredients, are the same. Otherwise, we cannot control that, like the effect of the pineapples. And back to our experiments, we need to control all the other variables, such as the mass of soil and the way we water those plants. And we also need to avoid cross-contamination. And as Bill mentioned before, hydroponics can make this process a lot easier.
Now we should focus back to data, and this will be a very interesting observation that we made. So essentially here are graphs that show us two different lead compounds sustain results. And as you can see, the difference in shapes of the lines could potentially mean different lead speciation. Now a little bit about how things works. So light and the beam essentially pass through gas atoms, and electrons are knocked off, which ionizes the atoms. Afterwards, a light intensity measurement is taken, and it uses a lower energy than the sample is expected to absorb. Then the energies increase slightly and the process repeats until the critical energy specific to each element is reached, and the light has enough energy to cause electron transitions, which is seen when a large amount of atoms is absorbed. This is a rise in the graph as shown right here. In the same scan, we can see different chemical forms of atoms in the sample. It can be critical for understanding chemical toxicity. And now this is our own example, which show that of course there will be some potential lead speciation, as again the lines have different shapes as circled out. There are conflicting opinions from experts. There is a possibility that the elements were previously bonded to the lead had changed, hence the speciation.
So lead is toxic. We mentioned that, and similar to pineapple on pizza, plants don't want to absorb it. So I have a couple pictures here of the dandelions before the first watering, and you can see that they're like very healthy, very green. All of the leaves are like above the edges of the pot, and they're in general doing very well. And this is a picture after they were watered with lead for the first time. So you can see they're less green. Part of that's the lighting, but also part of that was like we observed that. And some of the leaves are starting to sort of fall below the edge of the pot. They're generally not as healthy as they were before the first watering. But after that, after the second watering, actually, which still did have lead in it, the plants actually managed to recover. And we thought that might have been because they were using one of a couple of defense mechanisms. Next slide, please. So the first one that we thought they might have been using was reduced uptake into the plant. So if lead is pineapple on pizza, then this is essentially the simplest method of avoiding the pineapple, which is just ordering a different kind of pizza next time, or even eating less of your Hawaiian pizza. And so we thought that was maybe one thing the plants might have been doing. The second thing is sequestration into vacuoles. Now that's a little bit of terminology there. Essentially, in terms of the metaphor, this is just picking all of the pineapples off of your pizza and putting them in like a pineapple resistant jar off to the side so that you can just eat the delicious ham pizza by itself. The third one, this is probably the most complicated terminology, is binding of lead by phytogelatins, glutathione, and amino acids, which is essentially detoxification. So in terms of the pineapple metaphor, this is like taking your Hawaiian pizza and like spraying it down with like an anti-pineapple chemical, so that you don't have to taste the pineapple, and it like nullifies the bad taste. And you can again just eat the ham pizza by itself. And the fourth one is synthesis of osmolite. So this is essentially the plant saying, okay, well, this is the only pizza I have. I'm starving. I have to eat something. I'm going to eat this pizza. But before I eat it, I'm going to put in like a mouth guard, right? So even though the pizza is going to taste bad, I won't be injured by the bad taste of the pineapples. And that's essentially like the mouth guard is what the osmolites would be. So we're not sure if the zanes that Andrew King mentioned is actually chemical change or not. There was some error, but if it was, then it would indicate the phytogelatin, so the anti-pineapple spray being used. And as he also mentioned, two experts we spoke to disagreed on whether or not this is what's seen in the data. One of them said, yes, that's chemical change, and one of them said, I'm not so sure. It could be interesting for another experiment to focus on this. So we had three main conclusions. The first one was a good pizza is made with good ingredients. So our samples, they were very heterogeneous. They had like chunks of lead in them, with the one particularly striking map actually had like almost 100 times more lead in that one bright spot compared to the rest of the like the black map. So a future experiment would probably need to use one of the methods that we suggested to ensure homogeneity of the samples so that we can actually compare them using the XRFs and the zanes. Number two was don't mix ingredients together. As we also mentioned, there's a bunch of cross-contamination between the samples. When we were preparing them, we actually optimized it for safety. So there was like a little bit of cross-contamination that we just had to let happen because we were dealing with very toxic materials. But a future experiment would also have to address that using one of the methods we suggested. And number three was plants maybe using the anti-pineapple spray when they're eating their pizza. Future experiment using like our good samples could probably find something interesting using the zane scans if there were like a lot of samples and they were all well prepared, and we could actually see whether or not there was the chemical change, and that could be really interesting for somebody else to do an experiment on.
We would like to thank everyone who have helped us throughout our project, and anyone else who we perhaps did not mention.
Thank you for listening, and we've come a long way, and we appreciate all the help. We believe it will be very useful for any future projects.
So is there any final questions before we end today's presentation? Yes.
Why did you dandelions?
So we actually had a discussion during the process of making our research question. And initially we weren't thinking of dandelions, we were thinking of something more traditionally edible, such as strawberries. However, strawberries we found was difficult to acquire, especially in the season that we were doing our experiment on. And dandelions were a good choice because people do eat dandelions and they are being eaten more and more, and they were easier to sample. So this is why we chose dandelions.
Also, I'm just going to add on to that. Dandelions are weeds, so they're very resilient in general. And we figured like a strawberry plant or a more conventional plant might not have been able to use those defense mechanisms I mentioned quite as effectively as dandelions did.
Okay, next question. So you said you didn't raise your plants from seeds. So how did you get your plants?
We basically use a shovel, go to the park, dig them up, put them in pot, change the soil, add lead. That's it.
Because I think one of the variables you accidentally introduced into your experiment, and I'm a physicist, so I'd like to minimize the number of variables in my experiment, is you seem to have plants at different growth stages. Now, obviously, at different growth stages, plants are gonna uptake things from the soil and the water differently. So, again, next time, I mean, you've obviously learned an awful lot about how sample prep is important. I also have to say that, we've been around these places since the 80s, and you get here and you've got to figure out how to feed yourself, and you can develop a food fixation. This is the most extreme manifestation of a food fixation I've seen in the industry.
After you harvested them, how long did you let them adapt to being in a pot before you started?
I think, so when we actually took them and placed them in the pots, they were dying. So we had to, we couldn't immediately put our lead solution in. I think we let them sit for 2 weeks.
I think
We let them sit for 2 weeks. Before we actually placed our lead solution in.
What was the lead solution?
Oh, yes. So we called it the death juice. We obtained lead chloride from the university across the street, which is University St. Mary's. And we dissolved 1.25 grams into 1 liter of distilled water. So we had a known concentration of this highly concentrated lead solution, and we actually just distilled it into different concentrations. In this case, it was 60 mils, 90 mils, 120 mils, 150 mil, ppm, sorry, 60 ppm, 90 ppm, 120 ppm, 150 ppm, 180 ppm, and 210 ppm.
We'll make sure each time when we water the plants, basically feeding them solutions, we feed them a fixed amount of water, but just with different concentration.
Straight up lead or lead something?
Lead chloride.
Lead dichloride. It was lead dichloride was like basically the most water soluble we could find. That was also like
Easily
accessible and cheap.
Yeah.
Yes.
So what do you take away from the fact that 2 experts looked at your data in very different answers?
Probably that science is probably really, sometimes science is unpredictable and it's difficult to acquire for certain what the data is showing. And probably you'll need many more samples and many more trials before you get a conclusive answer.
I think this different perspective is needed for science.
Yes.
Okay, I always get the last question. So is this the last question? You have one? Go ahead.
When you did your mapping, did you put specifically with the roots, did you put them in a specific way? Like I imagine the lead would absorb from the edge of the root and then inward. I'm just wondering if like that could explain kind of what you saw.
So for mapping, it's the width of the roots actually do matter. I think it penetrates, it's like the amount of matter that's behind the slit. So what we did was we tried to make sure the width of each sample of the roots was even throughout the samples. So, and for the mapping, it's not just one section, it's the entire sample, but it's split up into different sections.
But it wasn't
If that
a
makes
cross
sense.
section.
It was across
Yeah,
that.
it was not a
No,
problem.
they weren't
Yeah.
big enough to do a cross section.
Yeah, the roots were like, they were like just a little bit wider than the slit that we had. So we chose like a specific part of the root that was like able to be consistent across plants, and we cut that. And that like basically fit in this slit perfectly. So there would have been like a little bit of like, I guess, width variation, which could have affected the maps. But
My turn? Okay. So it is obvious that you guys learned lots about designing an experiment and XRFs and dandelions and lead and all of that kind of stuff. But you've also mentioned learning about how to work your way through analyzing data and working together and doing things. My question to you is, considering everything that you've gone through from the start of this, which was a long time ago in the middle of the pandemic, right? To now, you're not quite finished yet. what stands out to you that you've learned that you can take forward with you as you take your next steps in education or going into your life over the next few years? And I'm going to ask each one of you to reply.
That's a big.
That's a
question.
really
It
good
is a
question.
big question. You can pause for a second, and when someone feels ready, you can feel free to
I
answer.
can go first. So, I think personally, I've learned that we should never jump to conclusions very quickly or set anything in stone because, of course, I think I'll mention even the choice of plant was perhaps an issue for us, and we changed that. We had many ideas, and for example, I think we mentioned this before, but we used lead chloride solution, and originally we might have thought that there was some other way. For example, using a nitric acid dissolve it, but afterwards we found, of course, lead chloride, which was way easier. And yeah, so I think from all the data analysis afterwards, it's very important that we look at all the data and look at as many correlations as we can find, and then to find almost a middle ground between conclusions and your initial sort of understanding, and just to present your observations and your initial sort of ideas instead of giving a full conclusion, which may or may not be fully accurate.
Can I go second? Yeah, so I'll go second. So for me, I think what I learned is real science takes a lot of time, and preparation is really important because that's the foundation of the whole experiment. So for us, we probably didn't manage to answer our research question, but we did learn that during our preparation of the samples, we sort of didn't do good enough to get our good samples. But probably the reason why is I personally think is we didn't have enough time. If you think about it, we didn't have a chance to raise plants from seeds. Therefore, they have like difference in between individuals, and that's probably one of the reasons why, as we mentioned in the presentation, that's the uncertainty. And then we didn't have lots of beam time. We did in one day. So yeah, I think real science takes patience and a lot of time. And you just have to make sure, especially preparation steps, they're really essential. Make sure you take time to build those.
I think for me, the most important lesson that I learned is always look back and review that what you have done and what you have did during this experiment, not only in the end of the whole experiment, but also in the middle and in between for each procedure. Because for us, because it took really long, it's a really long process, and we didn't actually review that probably the uncertainties or errors that we made during our procedures. So when we actually got the results, we were quite disappointed because we didn't find that exact correlation that we expected to have. However, when we were actually doing the slides and preparing for the presentation, we're actually analyzing our data, we found out that we had actually made quite a lot of uncertainties were mistakes, I can say. So I think for me, the most important lesson I learned is always look back and make plans.
I think for me, on a similar note to what Sean and Bill has said, I think I learned the difference between school labs and actual labs. So rather than having all of the steps and the procedure already planned out for you and already the trials have done so many times already that it's already confirmed, I think it's important to learn that a real procedure will usually have mistakes and you will need to review so many times and problem solve for every problem that you encounter. I think we mentioned, we didn't mention that we tried to make the lead solution twice. So the first time we put it into regular tap water because we've been using tap water to water the plants earlier, but the lead chloride just didn't dissolve. And we couldn't measure the concentration of the lead tap water because we couldn't measure the mass of the lead that actually dissolved. So for that, we problem solved through, we did a lot more research. We talked to some of our, the professors at SMU, and we figured that actual pure distilled water would work better, and it did. So I think that the biggest takeaway is to not rely on predetermined methods and make sure to put your own opinion on what you're actually experimenting on.
I can go next. sort of on a similar note to what Xinghua said, I think probably the biggest takeaway for me was like, okay, so we essentially didn't really make any big decisions individually, like we all tried to come together as a group and try and get everybody's input before we made a decision that like, you know, would have affected the experiment. And so I think in science, that's like really important, like having a lot of perspectives there. There were several times when I was like 100% sure that I was making the right choice, and I managed to convince a couple of people, and that was the decision we made. And there were a couple of times when I was really 100% sure I was making the right decision, and I really wasn't, and they managed to convince me otherwise. And I think that was a really important part of the process. Even like the two experts that we spoke to that disagreed on whether or not the Zane's scan showed results was like, you know, you need multiple perspectives on everything to get that. And yeah, like we didn't even like decide what to eat without like consulting everybody. It was just yeah, a really important part of the process with the democracy and the multiple perspectives. And yeah, I think that was important.
So I guess like most of stuff we were already mentioned, like the thing that I can add. So we did like all of this like in just like one day, and the importance of the teamwork that we had. So the division of the work. So we don't really have the like that much reliable data, but we at least we could like we interpret and we assess our project in just like a day, and which is important to us. Like we could do it and as a teamwork. If we like, for example, last night we were on like in one room, and then like that all showed me like the how the teamwork can speed up the work, and it's important in the process. And it's kind of already mentioned by Adam.
I would say that I'm sure everyone has also realized this, that the way in which we learn, no matter where we are, is limitless. We all learned that science is unpredictable, not to expect the expected, expect the unexpected, and that really in the end, experiments lead to discoveries. Experiments might lead to nothing, we don't know. So again, back to our main point, where we really hope that this project will perhaps be the starting stone for something much larger in the future.
Well, I'm very proud of you guys. You did very, very well. And yes, asking scientists to even give an update on their results a day and a bit after their beam time is, I think the term was ridiculous, but you did it. You did very, very well. So before we sign off, I'm going to make Mr. Bavena also answer a question. So you have brought several groups to students on the Beamlines, and I'm wondering if you could add some insights from a teacher's perspective about sort of what you've seen that might be different, or what you've learned from having the opportunity to bring several different groups.
That's a really good question. So particularly with this group, I think it's maybe rethink about the prescribed labs that we do in our course, and how these labs are perfect and how they work every single time. Maybe it is time to throw in some labs that spur the uncertainty that require the students to think outside the box. Because we always go into a lab, we collect our data, and boom, the results are perfect. And if they're not, you guys tamper with the results and bring about some form of certainty. But maybe it is time to put more of the unknown into our lab, into our classrooms. That's just something to think about.
Anything else?
I think this is it. Thank
All
you,
right.
everyone.
Then thank you.
Thank you, everyone.
What did you just realize?
Remember, like the how much are we going, Austin?
Yeah.
Probably from tablet.
That's possible.